So, shall we start? Let me turn off the lights. So, don't want this. No, it's fine. Okay, hi everybody. How you doing? Everything's fine. So, you remember what we did on last Thursday. So, we talked about backpropagation, if you remember. So, the key idea was that, or the main purpose, the main task we were doing was to compute derivatives on the computation graph. And what was the computation graph? It was a kind of graph which shows how a bunch of variables are related to each other, right? So if we start with one variable that's going to go through some function, you get the next variable. Then it goes through another function, you get another variable, and so on until you get to the end. And then the question is that, what if you want to compute the gradient of, or the derivative of the very output with respect to, for example, very input, right? And then we saw some simple examples. Oh, that one is easy. So we saw some simple examples, and we started with doing it like a scalar form. So every single entry was a scalar variable, but then we somehow concluded it into this vectorized form where you have a variable like z, which is a vector of variables, pass through some sort of function, and then you get another vector, and then you can keep on potentially as long as you want till you end up with one output, last output. And what we wanted to do, we wanted to calculate the derivative of the last output with respect to any guy on this graph, right? And this was what we did with backpropagation. Now, just a quick recap on this particular graph. So we consider three important operations. So we call them like local operations, 1, 2, 3. And these local operations, I mean, we still have not done anything on the neural network, right? We just consider that we have a function like r hat, which is computed directly from some vector y. And what we do know is that this vector y is coming from another variable like z. And what we wanted to do, we wanted to see if we already know what is the gradient of this r hat with respect to y, how we can get from this guy the gradient of r hat with respect to z. Correct? So this was the first case. In the first case, we assume that this guy is a entry-wise function, meaning that this f is going to be operated on every single entry inside z and gives you the corresponding entry on y. So if I want to move backward here, what should I do? If I do know the gradient of r hat with respect to y, how can I calculate the gradient of r hat with respect to z? What should I do? Do you remember what we do? Yeah, and what was the particular kind of product we do here? So what was, first of all, what is this particular link, backward link, from y to z? How do we get from y to z? So every single guy in z, look at it here. So z is a vector of this form, for example, z1 till zn. And then every single of them is being passed through function f, giving you y. So for example, y1 is f of z1, y2 is f of z2, and so on. So if you want to move back, what do? Entry-wise product to the derivative of f. So we just did this together, and then we ended up with this conclusion. So if I want to calculate the gradient of r hat with respect to z, and if I do know what is the gradient of r hat with respect to y, the only thing that I need to do is to just multiply entry-wise every single entry on this gradient with the derivative of f, this derivative of f dot, at the particular point z. Clear? You remember? And you remember that we said that whenever we do backpropagation, before that we have done what? Forward pass, right? So before we just go backward, we have gone forward, meaning that we started with z, we computed y, then we computed r hat. Now we are back. We already know this gradient, and if we want to calculate the next gradient, the only thing is that we calculate f dot at the particular point z, which we have already computed in the forward pass. You remember that? Everything's fine? I mean, if you don't remember, just let me know, because I'm going to use it today. OK, cool. So this was one case, one local operation. The other local operation was this guy. So here we have one vector z, and this vector z is multiplied with one matrix A to give us y. And then y has gone through something. We don't know what that is right now. And it has given us r hat. What we do know is that the gradient of r hat with respect to this y. And now if we want to compute the gradient of r hat with respect to z, what should we do? We do another kind of multiplication. What was that? A transpose. Great. Yeah? So the thing that you need to do is to just multiply it to A transpose, right? So you do know what is the gradient of r hat with respect to y, so you do have this guy. And then once you have this guy, you multiply it with A transpose, right? And we talked about this, that this can be always remembered using the dimension, right? So here dimension of z is k, dimension of y is n. A itself is k times n, so if you want to move backward, you need something n times k, which is going to be the transpose version, right? Everybody's clear? Any question? So that was the case for the second local operation. Then the last local operation we discussed was that we start from one matrix A. So A is now the variable. We multiply it to x. X is now the transform. So A times x is giving us y. And then this y is passed through something. Again, we don't care. It gives us r hat. And now what we do have is the gradient of r hat with respect to y. What we are interested in is the gradient of r hat with respect to this matrix A. And how do we calculate that again? Outer product. Great. So we do the outer product here. So again, you can always remember it by dimension comparison, because you have here a matrix, and then when you compute the gradient with respect to a matrix, it must be a matrix. You have one vector, which is the gradient of your r hat with respect to y. You have another vector, which is x. So if you outer product them, you're going to get the same dimensional matrix, right? Everybody's clear? So you don't need to remember the details. The key point is that you remember how I can get backward. So the moral of the story should be clear for you if you want to go forward. OK, so then, now that we do know these three operations, what we can do, we can simply move backward on any, or do the backpropagation on any fully connected feedforward neural network. So how we can do it? Let's start with the standard form that we just concluded in the end of forward pass when we were talking about the feedforward neural network. So do you remember what this means here? What is x here? Is input to your neural network, right? And then x is getting multiplied with W1. W1 was what? Weight of the first layer. Great. And then you pass it through F1, which is the activation. And then you again multiply it with the second layer weights. And then you again pass it through the next activation. And you keep on going like that, right? Till you get to your very output. this YL plus 1 was the output of your output layer, the last layer you had, right? And then when you start with doing forward pass, what you do, you start with X and you pass it through all of those transforms, right? So you start with X, you multiply it with W1, you're going to get your Z1, the first guy before activation, right? And then Z1 is going to be passed through function F, which is going to give you the first activated output, right? Then Y1 is again given to the next layer, which first multiplies everything with W2, the second matrix of weights, and then again you activate it. And you keep on going like this till you get your output, right? Now, what do we want to compute in backpropagation? The gradient of the loss with respect to weight matrices, right? So what we want to compute is that we do know that we have, for example, we talked about this, we have one single input right now. We have one single input, we give it to a neural network. It's going to pass through all these layers, and it's going to give us some output. We do know the true label V, so we are going to compute the loss between the output and the true label, right? And then we're going to get R hat. And what we want to compute is a gradient of R hat with respect to all the weight matrices that we have. Clear? Everybody's clear? So we pass forward, and when we pass forward, we compute every single node in this computation graph. So we compute Z1, Y1, ZL, YL till the last guy, and we even are able to compute R hat because we do have the true label. We do have the output, we can compute the R hat. And now the next thing we want to do is to compute the gradient of this R hat with respect to every single entry in this, or every single weight matrix in this network. Okay? Okay. So let's go ahead, say that we have finished forward pass, so we have the value of every single entry here. And now let's say we want to start with the first weight matrix, which is the weight matrix of the very last layer, because we are now moving backward, right? So we are moving from very end, and the first weight matrix that in the backward pass is going to show up is the weight matrix of the last layer. Clear? So I want to compute that one. And we do know every details that we need in order to do that with backpropagation. So let me first cut this computation graph exactly at the point where WL plus 1 shows up. Okay? So I'm going to just start from YL plus 1 because I don't care about anything before it yet. Okay? The only thing that I want to compute is the gradient with respect to WL plus 1. Okay? So I'm going to cut the graph at this point, and this is going to be the remaining graph, right? Now, let's recall, first of all, that what the variable is. The variable that we want to compute the gradient with respect to is this weight matrix. Okay? So is this graph showing you the right format that we were showing our computation graph when we wanted to do backward propagation?
Is it showing the right format?
The right form. Were we just using the same thing when we wanted? I mean, usually when we wanted to compute the backward pass, or we wanted to compute the gradient, we just look at the variable and start everything with the variable, right? Do we start here with the variable?
I guess you need to do the forward pass first.
No, we have done that. We do know everything. Now, my question is, just look at this graph. If I tell you to compute the gradient of R hat with respect to WL plus 1, given the previous slides, do you feel this graph is a right graph? No. What should I do?
Swap the y and up.
Exactly. So in all the graphs that I showed you, when I wanted to compute the gradient with respect to a variable, I put that variable to be a node, right? So here, your weight is not a node yet, right? But that is a very easy thing to do, correct? So you could say that, okay, ZL plus 1 is basically WL plus 1 times YL. So instead of looking at WL plus 1 as the transform and YL as the variable, we can just sweep everything, right? So what we can say WL plus 1 is know the variable, and then the thing that is transforming it is this YL. So I multiply this guy to YL. I'm going to get this ZL plus 1, and everything is as before, right?
I'm so sorry for bothering. Can we guys see a water bottle here? Like somewhere in the front?
No. What is the color?
It was like this big of a water bottle, beige, like
No, it's not here. No problem. So now look at this guy, and now what we want to do, we want to just get back from R hat to this guy, right? Okay. Now, first of all, if I want to get back, the first path that I should go over is from R hat to my next variable, which is YL plus 1. Can I compute the gradient of R hat with respect to YL plus 1?
With respect to YL plus 1?
Yes. So I have R hat to be the loss function of YL plus 1 and that true label V, right? Now I want to compute the gradient of R hat with respect to YL plus 1. Can I do that? No. Yes, because I just need to compute the partial derivative of the loss function with respect to every entry here. And I do know how to do that because I do know what is my loss function. Yeah? For example, that is MSE, meaning that this is basically YL, the norm of YL minus V squared. And if this is my loss function, then I simply can compute the derivative of this guy with respect to every entry here, right? Just open it up, do the derivation. So I can compute this gradient from here. So the first thing is to compute this gradient, and I do compute the gradient. So I do know what this guy is, right? Correct? Now I do know the gradient of R hat with respect to YL plus 1. The next thing that I want to know is what is the gradient of R hat with respect to ZL plus 1. What should I do? Sorry? F, exactly. Entry-wise product with that gradient, exactly. So the next thing that I can do, I can just compute the derivative of this FL plus 1, F dot, and then compute it at the point ZL plus 1, and then do the entry-wise product, right? This is your first local operation, correct? So if you do know, just once again, if you do know what is this gradient, and you just want to compute the gradient of R hat with respect to Z, the only thing that you need to do is to just do entry-wise product. Yeah, this was the first local operation we talked about, right? So the next thing that I do, I'm going to get this gradient, which I could compute because I do know my loss function, and I do entry-wise product with the derivative of activation function. Clear? Everybody's clear? Now, the next thing that I want to do, I want to get back from ZL plus 1 to WL plus 1. Can I do that? What do I have right now? I do have the gradient of R hat with respect to ZL plus 1, right? I do have that because I have computed it here, right? And now if I just simplify this graph for you, this is going to look like this. So it's going to be WL plus 1, and then you have YL, and then you have your ZL plus 1, and then at the output, I mean, when you pass over everything, you're going to get R hat. And you do know what is the gradient of R hat with respect to ZL plus 1, right? We computed that one. How can I compute the gradient of R hat with respect to WL plus 1 then? Exactly. So I just need to multiply everything with YL transpose, right? So this is going to be the next step. So I am going to get this gradient which I computed at this node, and then I'm going to multiply it with YL transpose to get the gradient with respect to the first weight matrix. Clear? Everybody's clear? Yeah? So, starting from R hat, I ended up computing this gradient, right? But what if I want to know also the gradient with respect to YL plus 1, YL plus 1, WL plus 1 I already computed. What if I want to compute the gradient with respect to the weight of the previous layer, WL? So, yeah?
I guess because you're going to have, in front of the WL, you're going to have YL and then ZL, so it's just going to chain all the way back.
Exactly. So we always are going to just cut it exactly where that weight matrix starts, and then we're going to keep doing this one till we end up with the first weight matrix, right? So, for example, so this is always the way that we do it. We just look at the particular gradient that, weight that we want to compute the gradient with respect to. We just cut the link at that point on the computation graph, and then we just do that swap, and then after that everything is as what I showed you here. So, for example, say I want to compute the gradient with respect to WL. What I'm going to say, okay, this is what I had up to this point, but now I keep YL as it was before. So if I look at this graph here, here. So what I want, WL is here before ZL, right? So I want to have this guy, so the only thing is that I just cut it before that ZL, right? And then I keep everything as before, then I just change those two variables at the very beginning of the graph. Clear? So what I'm going to do here, I am going to have these guys as before, then I just change WL and ZL. And then how can I get from WL to ZL? YL minus 1, exactly. So I'm going to multiply WL to YL minus 1. It's going to be ZL, and then ZL going to be activated, again transform, again activated, and then we compute the loss. Clear? So you got the idea what I'm doing? So now this is the computation graph, and I already have done the whole forward pass, so I do know what is every single entry here. I just need to move backward on this graph. Clear? Now, let's do it together. Do I need to start from R hat? No, because I already did compute these two gradients in the previous step, right? When I wanted to compute the gradient with respect to WL plus 1, I already did the backward pass to YL plus 1, ZL plus 1, right? Now, the next thing is that I get from this ZL plus 1 to YL. And again, you look at it the same thing as here. So let me just show you again. So say that I have YL here, and then I do have ZL plus 1 here. Yeah, that is itself, ZL plus 1. So I just look at YL, and then ZL plus 1, and anything after that, I just assume it's a kind of transform. I'm going to end up with R hat. Now, I do know what is the gradient of R hat with respect to ZL plus 1, because I already computed it in the previous step, right? Now, this guy, YL, is getting to ZL plus 1 by getting multiplied with WL. How can I move backwards here? WL? Sorry? Sorry, WL plus 1. Right. Sorry. Thanks. So I just move with WL plus 1 forward. How should I move backward? Just multiply with the transpose, right? So it's going to be WL plus 1 transpose, right? So I already know what is this gradient with respect to ZL plus 1. The first thing that I'm going to do is multiplying that gradient with WL plus 1 transpose. Then I'm going to get the gradient with respect to YL, right? And then the next thing is that I am going to just get this YL, this gradient with respect to YL, and then I just move backward to ZL, which is again an entry-wise product, because The forward pass is an entry-wise function, right? So again, local operation 1. And I do know this guy, and I'm pretty sure that you do know what you should do to get from ZL to WL, yeah? Just the outer product, right? So just one tiny point here. What is the dimension of YL? And just to keep everything simple, say we have 10 neurons in layer L. 10 neurons in that layer. What is the dimension of YL? 10 by 1? When we were doing forward pass, we were always getting rid of bias. How do we get rid of bias? We just add dummy variable 1, right?
11.
Yeah, so it's going to be 11. So, but should I really care about the gradient with respect to that dummy variable? No, it's not going to change, right? So this is just a tiny point. You always drop that guy. So like when you do in the forward pass, you add that dummy variable. When you get backward, you just get rid of that dummy variable. It's not going to do anything for you. Yeah? Clear? Now, and again, you can just justify it by looking into the dimension, right? Because here this YL is of size 11, but ZL is of size 10, right? ZL is not of size 11. You just first do the transform, and then you add the dummy variable, right? So just to match the dimension, you need to do that, okay? So you just get rid of that 0 entry, which is, or entry at index 0, which is not useful. I mean, it's not going to do anything for you. And then after that, you do repeat the third local operation. So you want to get back from ZL to WL, you simply multiply it and compute the outer product with YL minus 1. Clear? So you can keep on doing it like that. So if you are in one particular layer L, you always end up with the same thing. So you have already computed the gradient up to ZL plus 1, and then you do 1 transpose, 1 entry-wise product, 1 outer product. And every time when you compute this guy, you just get rid of the 0 entry. In the forward pass, you just add that entry, that dummy entry. In the backward pass, you just get rid of it. That's it. Okay? And if you keep on doing it till you get to your very first layer, then you have the gradient with respect to all the weights. Everybody's clear? Yeah? Any question? I mean, you don't ask question, but you also don't look very friendly today. So. No, it was a long day. Okay. So it's not about me. I shouldn't take it personal. Okay, great. Okay. So, cool. So I hope that this is very clear for you. I just try my best to break it out, break it down for you into like details so that you understand how you really compute those gradients. Now, one thing that you can do is that you can just show that if you just write it down in form of an algorithm, it is exactly a dual form of your forward pass. How we can do it, just to make the notation like simple for you, I'm going to define this YL dash to be the gradient of R hat with respect to YL. Okay? So YL dash, when I show dash, I mainly mean gradient. And one thing that you should pay attention, YL and YL dash are two different things, right? They are of the same dimension, but they are two different things. One of them is what you compute in the forward pass. The other one is the gradient of your loss with respect to that guy, which is a different thing. It could be totally different, but they are of the same dimension. So let me just define these two things, YL dash and ZL dash in this form. And now, if I want to just write down a pseudocode for this backward propagation, the first thing that I can do is that I can just write down the very first computation that I do. So my very first computation is to just compute the gradient of the loss, which I can consider it as a kind of initialization of these dash values. And then the YL dash is initiated by this gradient of the loss, and ZL dash is simply initiated with that gradient that you have computed before, this YL plus 1 dash. times entry-wise times the last activation function, right? So this is what you do to initiate those y and z dash values. And once you do that, now you start, you can actually immediately here compute the gradient with respect to your output layer weights, right? So if you put this small l here to be l plus 1, then you basically just need this gradient with respect to zl plus 1, which is zl plus 1 dash, and you multiply it to the y of the previous layer, which is going to be, in this particular case, it's going to be y capital L transpose, right? So this is what we did in this, couple of slides. This is going to be the gradient with respect to your output layer. And if you want to keep on going for your previous layers, the thing that you are going to do is that you just keep going backward. So you go to the layer L. In each layer, you first compute this transpose, because, in the forward, you first compute the linear transform, right? And then you just multiply that transpose of the linear transform, and you multiply it with the ZL plus 1, which you got from the previous, or the next layer actually, or your previous gradient computation. Then you just drop the 0 entry, the entry at index 0. Now you have the gradient with respect to YL. And then if you just want to keep on going for the previous layer, or you want to just find out what is the gradient with respect to z of the previous layer, you simply just need to multiply everything with the entry-wise transform, right? And once you have done, after every single layer computation, you can compute the gradient with respect to the weight of that layer in this form. Yeah? You just need to know ZL dash. Once you have ZL dash, you just multiply it with y L minus 1 transform, so one outer product, and it's going to give you the gradient. Clear? So nothing is specific, exactly what we did before. I just put it in the form of a pseudocode, an algorithm. And now, one thing that you can pay attention here is that you basically don't need to compute the gradient with respect to weights after every, in each layer. You can just move completely backward over your whole network to get to the very input. And at that point, you have all the things you need to compute the gradient, right? Because I really don't need to do it immediately here. What I do need to compute the gradient, for example, with respect to the output layer, is to know this guy, ZL plus 1 dash, and YL, right? And I can keep on going till I know ZL dash for every layer L. And once I do have it, then I can just compute the whole gradients all together, right? So in other words, I don't really need to put this loop inside that loop. I just can do them separately. Just go backward till you get to the input, and now you are able to compute all the gradients. Now, this guy, I'm not sure if you see it right now, but if you remember, the forward pass is the dual form of the forward pass we had. Okay? So if you look at this guy, it's going to be very similar to what we had in the forward pass. And if I want to just show it to you, I can just put them next to each other. So in the forward pass, we initiate like the output of the 0 layer, which is basically your input layer, with your data. Here what you do, you just initiate your ZL plus 1 dash, or the gradient of the very last layer, with the gradient of your loss function. And then there you keep on going. You just add one dummy variable, do a linear transform, activate it. Now what you do here is that you just do the transpose of the similar linear transform. You get rid of that dummy variable, and then you again do the gradient of the activation, which is entry-wise product. And then finally, here you're going to write out what are those variables YL and ZL, and here you basically can use them to compute the gradient with respect to the weights. Clear? Any questions? Yes? Sorry? Initialization, when you start with the very first, here. When you start with R hat, if you want to just compute your very first gradient, you need to compute the gradient with respect to loss function, right? So we said here, like your r hat is always written in this form. So it's going to be the very last output. You just compare it to your label, and then you compute loss, right? Now, if you want to compute the gradient of r hat with respect to yl plus 1, you can basically use the definition of your loss function, depending on what your loss function is. And then you compute the partial derivative of r hat with respect to the first entry in this, first entry in this guy, in this vector yl plus 1. Then you compute the partial derivative with respect to the second entry in yl plus 1, and so on till the last entry, right? But that one, you need to do it somehow by hand. Yeah, you need to define it because you need to know what is your loss, and then you define this gradient, partial derivative, which is the partial derivative of your loss function, and then you're going to have this vector. So once you have this vector, then anything else is just going to be backward pass. Clear? Any questions? So you got the idea how you can go forward and backward? Great. So if you want to compute a gradient, what you need to do, you need to start with your data point. You move all the way forward to the output, and then from the output, you move all the way backward to the input again. And the forward pass, you are computing the values of every single node, every single layer, and use those values so that you can, in the backward pass, compute the gradients, right? Cool. So now, if I want to just wrap up everything inside the gradient descent algorithm, which we were using to optimize our loss function or our empirical risk, how can I do it? Say I have a data set and I have b different data points inside it, right? I have this guy. What we do in gradient descent, we come, yes? Sorry.
You do the backpropagation since you have all the weight, the derivative of all the gradients with respect to weight for each layer, I guess for each layer, or for all WL plus 1, you could just find the average of the gradients of each.
Exactly. We need to just average them, exactly. So what we do here in the gradient descent, if we right now don't think about the backpropagation, what we want to do, we just compute the risk function, right? And the empirical risk was basically the average of the loss for every single point. Yeah? We compute that guy, and then we try to minimize it. But if we want to minimize it, we just the only way that we know to do it, we just compute the gradient of that empirical risk, and then we subtract it from the previous weight, and we keep on doing it till we converge, right? So this was the gradient descent. Now, if you want to just fit in the forward and backward pass into this algorithm, what should we do? We initiate everything with some weights. So weight of every layer is some random thing. You just generate it randomly. And now that you have that random weight, the first thing that you need to do is to just compute the gradients, right? And if you want to compute the gradient, you remember that this forward-backward pass was to compute the gradient of the loss for one single point, one of those x and v's, right? But now here you have b different guys. And we talked about this, that if you want to compute the gradient of the risk, the only thing that you need to do is to compute the gradient of the loss with respect at every single point, and then average everything. So this is going to be what you need to do with forward-backward pass. So you just do the forward pass with one single point and the given weight. So like in the very first iteration, it's going to be your initial weight. And you compute all the values inside your neural network. This is going to be your forward pass to the end. And then once over, you're going to just do backward pass from the very output. You get backward to the very input. And at that point, you can compute the gradient of the loss with respect to every single weight inside your neural network. But what you have done is just to compute that gradient for one single point inside your data set. If you want to compute the gradient with respect to the empirical risk, which is the average of those guys, you need to compute that, do this forward and backward for every single point inside your data set, and then you average those gradients. So you just start with the first point, you just go forward, backward, you get the gradient for the first point, second point, third point, till the very last one, and then what you're going to do, you're going to average all of those computations. So you got your first, so you see I am showing it with RB, which is the loss computed at the particular point x, b, and vb, right? And then I'm going to just average these gradients that I have computed for 1 to b, first to the last point, and now I can do just one step of gradient descent. Clear? And now I have a new weight. I again go up. I again do all the forward propagation, backward propagation for every single point. I get another bunch of gradients. I average them out. I do another step of gradient descent. And I keep on doing till I converge. And you can imagine that it is a very exhaustive thing to do. And we're going to get rid of that huge complexity by going for a stochastic gradient descent shortly. But this is the main idea. Clear? Yep.
Why can we generate the new weights with different gradients? Why do we need to have a mean gradient?
Mean gradient because we talked about this before, like your empirical risk, if you talk about the empirical risk R hat, that is written as the summation. I mean, you write it down 1 over b, the whole points that you have inside your data set, summation b from 1 to b, those R hat of b, right? Is it correct? So this R hat of b is basically the loss that you compute between the output of your neural network, say yl plus 1, for the particular point b, when you put xb inside your neural network, and the true label of your point, right? So this is what you compute, and I just called everything here RB, R hat b, sorry. So this is R hat b. Now if I want to compute, when we develop the gradient descent algorithm, we said that we just start with one WT, and every time for the that we want to update it, we're going to get WT and subtract it from some learning rate times the gradient of the gradient of R hat with respect to WT, and then we're going to call this WT plus 1, right? This one, this is the gradient descent. Now, you need to know the gradient of R hat, right? And if you want to know that, the gradient of R hat is going to be 1 over b summation of all those gradients, right? So each time you go forward and backward, you are just computing one of these. So you need to do b different times to get all those single point gradients, and then you just average everything out. Yeah, this is basically averaging. So by mean, I simply mean this guy. So instead of this, I'm just writing down mean. Okay? And then now that you computed the mean value, then you have one gradient. And that gradient helps you to just update your weight. Now you get the new guy. Again, with this new guy, you need to compute this one. And to compute this one, you need to just do b other forward-backward paths. Clear? So, everybody's cool? Was it interesting enough? Or, yeah? So, I see your faces, and many people, like before 2010, had the same faces. So they were saying, okay, that sounds very nice, but it's not going to work. But it apparently worked, yeah? So it works nowadays. So, yes?
I have a question. We get the gradient, am I right?
Yes.
And we have a function such as rho, which is nonlinear.
Yes.
How can we get the gradient?
So for that one, we have no problem.
Or something like that, and we have a nonlinear function.
Nonlinear, or you mean
Yeah.
non-differentiable?
Yeah.
So that one we said we can compute the subgradient, right? Yeah, we can do that. But your other question is the non-continuous ones.
Yeah.
And these are the ones which we don't like, but in that case, if in extreme case we do that, we said that we just use the sign of the gradient. Yeah, that's it. Yeah. So instead of those f dots, you put either subgradient or the sign of your gradient.
And
Or
for subgradient, you mean that, for example, we are just trying to get closer to the point which we want if we are getting in a non-differentiable?
exactly, exactly. This is the only information you can collect in that case. And they are not favorable. I mean, we're going to get rid of them quickly. But if you are working with them, I mean, you can nowadays implement that by PyTorch. And this is, you just simply follow the sign. So, any question? No question. Okay, so 656, we start 7 with classification, right? Okay, so we're going to use everything to just start with a real example. Thanks. So shall we go on? So now that we do know how to do the backpropagation and we do know how we can compute the gradient, now we can simply train a neural network for one particular task. And the best thing we can start with is to just start with a simple classification problem. So what is the classification problem that we are going to look into? Is that we have a set of handwritten numbers. These are handwritten, like the zeros on top are the handwritten numbers by some people, so they have written 0, different kinds of 0, and 1, 2, 3, and so on. And we want to just train a neural network which can tell us, looks at the pixels of one image and tells us whether that image is handwritten number 2 or not. Okay? So I'm giving it either 0, 1, 2, 3, anything, and it's going to tell me whether this image is handwritten 2 or not. What kind of classification problem is that? It's binary classification, exactly. This is a binary classification because you just have two classes. One class is that this handwritten number is number 2. One class is that this handwritten number is not number 2, right? So this is a binary classification, and your data set is going to look like this, right? So what is XB here in this data set? Is the pixel vector, right? So you just go ahead, look at that image, and then say your image is, I don't know, it's an MNIST image, so it's 20. We're going to talk about this. 28 times 28. So 28 pixels, like vertical, 28 horizontal segments, and then you have in total 734. Yeah, 734 different pixels, right? And then you have one vector of that dimension, that big dimension. And then they are all collected inside this XB. So you have seen it already in your assignment 1. And what about VB? What is that? It's 2 or not. So if it is image of 2, then you're going to say 1. The label is 1. And if it is not image of 2, then it's going to be, if it is handwritten 2, it's going to be 1. The label is going to be 1. If it is not handwritten 2, it's going to be label 0. What does it mean? It means that you go over data set, you look at every single image by your eyes, and you see this is not 2, so you're going to put the label 0. And then you go for the next image, you see that this is 2, you're going to put the label 1. This is the only way you can label it. Okay? So this is your label, which is binary. Your input is a vector of pixels, which is of a particular dimension. Right now we assume it is of dimension n. And then you have this whole bunch of data, which is your data set. And from now on, in this lecture in particular, I'm going to call this data that you have collected to train your neural network the batch of data. And I do know some of you with background think that, okay, batch means a small thing. That is for me mini batch. So don't get mistaken. So I just put the first stone here. Batch is the whole data that you have. Okay? Clear? Now, what you want to do, you want to just make one neural network which does this job for you, meaning that you get one neural network, it has a bunch of weights, and then you just keep on going forward, backward over that neural network till it gets trained. And at that point, you hope that if you get a new handwritten image of the same format, of the same dimension, number of pixels, you just give it to this neural network, and it's going to predict for you correctly whether it is 2 or not. Okay? So, first of all, I just need to specify my fully connected feedforward neural network. So what are the hyperparameters? I want it to be deep. So I need to have at least 2 hidden layers, because one hidden layer is a shallow neural network. So I'm going to put only 2 hidden layers for simplicity right now. And then the next thing is that I need to specify the size or the width of every hidden layer, right? So we used to just have those, inconvenient notations like W1, W2. Since it is just 2 hidden layers. I'm going to just use K and J. That's going to be much easier now. So what is going to happen is that I have my data X. So this data is of some dimension n. And this is going to just get to the first hidden layer. So in your first hidden layer, you have here, K different neurons. So this is your neuron number 1, neuron number 2, neuron number 3, so on till neuron number K, right? So this guy is K, 1, 2, 3, and so on till K. And every single input, so your input is of this form, so it is x1, or I write it here, x1, x2, and so on till xn. These guys are all connected to each other, right? So this is, all of them are connected to the first neuron. Again, all of them are connected to the second neuron, and so on till the last guy, yeah? So the last guy also gets everything from everybody. And the next thing that I'm going to have is one other layer. So that layer is of dimension j. So here is 1, 2, and so on till j. And again, everybody is going to be connected, right? So everybody is connected to these neurons from the previous layers, and so on. And then at the very end, I have one output layer. And what is the dimension of that output layer? You say it? 1. Why? Because I have one label, right? My label is either 0 or 1. So I am going to have one label, V, and then I have just one neuron here. And I connect every guy here in the second hidden layer to this one. And then this is going to give me one output Y. What I hope is that this Y is going to be correctly telling me whether my input is handwritten 2 or handwritten number 2 or not. Okay? Clear? So that is the architecture of my neural network. I am going to use for my hidden layers always the ReLU function. So everybody here in between, so in this and this layer, every guy has been activated by ReLU function. So I just show it by R to make it simple. And since I have a binary classification, I need at the output to have either 0 or 1. So I'm going to put one perceptron at the output. Clear? So this guy is simply a perceptron. So I have one perceptron here, gets this number. What it returns is either 0 or 1. Clear? So that's going to be the model. So basically what I showed there for you. So I have the first layer, layer 0, which is the input layer. And this guy has n different inputs. They are going to get connected to the first hidden layer, second hidden layer. And then you have your output, which is a perceptron. Clear? So your model is now fitting the problem that you have, right? You could have come up with another model. Yeah? You could have made it deeper, right? But I mean, this is a kind of, obvious choice. Yeah? Now, we have this guy, and let's see what we need to learn here. So what do we need to learn, basically? So I need to learn the weights here. And what is it? Is a vector of weights, right? Is a vector of weights, because you have only one perceptron here, right? So you have all the weights for the perceptron and the bias on top of that, right? And what about this here in the second, the one which connects the first to the second hidden layer? Here you have a matrix of weights, right? And what about this one? Again, a matrix of weights, right? So you basically need to learn two matrices of weights and one vector of weights at the output. So these are the parameters you need to weight. So in the first layer, you have n input. You have k neurons in your first hidden layer. So it's going to be n plus 1. That plus 1 is simply for the bias. N plus 1 times k links. So because of that, you have nk weights and k different biases, or in general, n plus 1 times k different weights. Yeah? Same thing going to be for your next layer. You have k neurons getting connected to j neurons. So it's going to be k plus 1 times j links, and every single of them has a weight. We need to learn all of them as well. And finally, your last layer is going to be j plus 1, which is these j different neurons plus one dummy variable here, which is the bias. And then you're going to connect all of them to a single perceptron, so you have a vector of weight, and you need to learn the entries in that vector as well, right? So these are all the things you need to learn. And the only way that you can do it is simply by doing gradient descent. And if you want to compute everything, you need to use forward and backward propagation. So so this is basically the same thing. I just put the dummy variables here to just indicate on the number of links that we have. And then finally, I need to specify my loss function because I need to compute the loss between my output. So when I send everything, I want to know what is the loss between this guy and the true label, right? And since I have one output which is a binary output, and my label is also a binary label, the best choice that remains for me right now is to simply use the indicator, error indicator, meaning that I just look at the output of my, my perceptron for the particular input xb. I look at that guy, and I compare it to the true label. If they are the same, I'm going to say the error is 0. If they are not the same, I'm going to say error is 1, right? And I do know that you would say, OK, you told us this is not a good choice. We're going to see it. I want you to see it, why it is not a good choice, right? Now, yeah, so this is what I said before. So you would say this is not a good choice, and I'm going to show you. You now can simply understand because you do know how to move forward and backward in this neural network. So let's just go ahead. I mean, I promise I'm not going to do that too much in the lectures. But let's do it once together. Just write down the computation graph to see how things are getting computed on this neural network. So if you have one particular xb, so this is one particular pixel vector, you're going to just fit it into your neural network. You do the first transform with the first weight matrix, you get z of the first hidden layer. It just gets activated by ReLU, you get y1. And then you do the same thing again. And finally, you just multiply everything with this matrix W, the last matrix here. So by W3 transpose, I simply means this last vector. And then you're going to get 1z3, which is a number, just a single number. And then you just pass it through the sign function, right? Because you have here perceptron. You remember how perceptron works, right? So you get everything. You just compute the linear transform, which means that you get your output y2 and multiply it, the inner product, with the weight vector. And after that, you get one number z3, and then you check the sign. If it is positive, you're going to say 1 at the output of the perceptron. If it is negative, you're going to return 0, right? So this is going to be a sign function. And then this y3 is going to be compared to the true label, yeah? So VB is the true label for this point. It's going to get compared through this loss function, which is your indicator function. And then after that, you're going to get one loss value here, which is either 1 or 0 for you. Clear? Now, if you want to do, so it's basically what I explained to you here. I just indicated the dimensions. So I think everything is obvious. So. And now, yeah, again, the same thing. So S is the sign or step function. So you're going to use the step function in your perceptron. And then if you want to do the training, you basically need to use the gradient descent with forward and backward pass. Yeah? And just we don't look at this whole complicated thing. We just start to do it. Yeah? So if I want to do it, first of all, let's just try to go forward together. We start with a pixel vector xb, right? I get xb. I just add one dummy variable on top of it, which is 1, right? And then I multiply it with the weight. And this weight is, I mean, initially I just generate this matrix randomly, okay? Just I generate the same dimension matrix. Randomly, I put number in it. And then I'm going to compute the first linear transform z1 after multiplying this extended vector into this weight matrix, right? So I'm going to get Z1. Clear? And then after I get Z1, I am going to activate it by ReLU function. And how does ReLU look like? It's going to be 0 when it's negative. It's going to be the same thing when it's positive, right? So it means that I look at Z1. Every single guy who is positive, I'm going to keep it as it is. Every single guy who is negative, I'm going to replace it with 0, right? This is what you do with ReLU. Clear? And now you have the activated version, so you have Y1, and you do the same thing again. You're going to get your Y1, you put one dummy variable on top of it, you do your linear transform, and then again you activate it by ReLU. You simply keep the positive guys, you just get rid of the negative guys, replace them by 0, right? And you keep doing that till you get to your second hidden layer, and then after that you simply pass it through the perceptron, meaning that again you add up this dummy 1, you compute one number which is inner product of these weights here with your extended output, and then after that you just pass it through the step function. If it is positive, you're going to say label is 1. If it is negative, you're going to say label is 0. And at this point, you do have Z1, Y1, Z2, Y2, Z3, Y3, and you are able to compute the loss. You just get your Y3, you compare it to the true label, and if they are the same, you say loss is 0. If they are not the same, you're going to say the loss is 1. Clear? So we pass forward, everything's fine. No magic, no trick here. Forward pass, right? Great. Now, we have every guy here. We have the input, every single entry in between, and the output. And the next thing that we need to do is to just move backward over this guy, right? So if I want to move backward, I need to initially compute this gradient here. And after that, every single operation here, I do know how to move backward. For every single guy here, for example, for this step function, I need to replace it with the derivative and do the entry-wise product. Here, I just need to multiply with the transpose version, and so on. And once that I computed all those gradients, or all those dashed versions of my y's and z's, then I can compute the gradient with respect to every single weight in this network. So that is going to basically be the backward pass. So you basically start with computing these guys, and you right now are seeing the problem, where the problem is going to be. So you are going to compute this derivative of loss with respect to y, which means that you need to compute the derivative of this indicator function with respect to input y. You also need to know what is the derivative of step function with respect to its argument. This is the second thing. And then you need to know what is the derivative of your ReLU function with respect to its argument. For the last guy, the derivative of the ReLU function, we talked about this, right? So we could compute it on the negative side. We could compute it on the positive side. At the particular point 0, we couldn't. We just replace it with subgradient, right? Any point between 0 and 1 was OK for us. Yeah? So that was what we defined as the subgradient. So I'm going to use that one to be the R dot, right? And now if I want to just do the backward, I'm going to start with just saying y3 dash is simply this L dot at point y3. And then I compute z3 dash from that one. Yeah? I just multiply it with the derivative of the step function. Now I have z3 dash. I am going to compute from z3 dash. I just multiply it with w3, which is the transpose of my forward pass transform. And now I get this y2 dash. This is now a vector. And now when I have y2 dash, I have this one dummy variable. So I'm going to get rid of that dummy variable. Now I have something of the exact size of my hidden layer. So now the size is j. Okay? And once I have done this, now I just compute the derivative of ReLU function at point z2 and do the entry-wise product, right? And you can keep on going like this. So again, from y1 you can compute z2 you can compute y1. Again, you remove the dummy variable, you compute z1. And once you have everything like that, then you can simply compute all of those gradients. That's it. Yeah? So I do know it was a bit boring, but this is what your computer do. Clear? Yeah.
It's notation time again.
Yeah, sure.
So in step 3, you have the transpose.
Yes.
Go back one slide.
Here?
Here, step 2, we're doing
Step
Y.
2. Yeah, but when you transpose everything, I mean, Z3 dash is a number, right? Z3 dash is a number. Its transpose is the same thing as itself. So it's going to be Z3 dash, and then when you just transpose everything, then you're going to see this expression, right?
Oh, right, okay, right, because W3 is a column.
Transpose, yes. I already transpose, yeah. Just wanted to make it match to the, because if you want to look at it as a matrix, you can look at it as a single row matrix. Sorry, yeah?
Oh, why is it a number though?
Sorry?
Why is these a number?
Because this is the linear transform of the perceptron, the final output, exactly. Yeah. So when you compute, here on your perceptron, yeah, come on, yeah, here. I mean, this is what you compute after multiplying these weights into your last layer. Yeah? You get a number and then you check the sign, right? So that's a number only. Okay, so, yeah, yes, sure. Sure, definitely.
Like for the backpropagation, how this gonna work? Because first of all, the step function is not.
Yeah, this is what I'm going to say next. yeah. So I just wanted to bring up this question to your mind. That's great that you mentioned that. Yeah. So, any question rather than the issue with the derivatives? No. Okay, great. So, very good point that your friend asked. So everything looks working right now. The only issue here is that how we can compute this L dot and S dot, right? How we can compute the derivative of the error indicator function and the step function. As all of you know that those functions are discontinuous. They are not possible to be differentiated. So that is an issue, and this is basically what I initially told you, that we are not interested in these functions. Because in that case, the only thing that you can do, you can only rely on the sign of the gradient. And this is then a quite questionable task to find out what is the sign, because you basically don't have any gradient. Only gradient you can imagine that is just going plus infinity or negative infinity. So how we can get rid of that issue, there is actually a very well-established trick that we always do in classification, and that is to just replace everything here with something that is differentiable. But we need to do a bit of modification here. So the first thing is that, let's start with that step function, which is a challenge. So we do know that this step function looks like this. So the step function looks like this. So it's going to start at 0 here, and then, so it's 0 here, and then it just jumps to 1 at this point, right? So this is your step function, S of z, if this is z. Now, do you remember of any function that looks like this one, but is smooth? The sigmoid function, great. So the sigmoid function is the same thing, but it's now differentiable. So this is the sigmoid function, right? So we talked about this one before. So let's just replace this guy with the sigmoid function. So sigmoid function is the smoothened version of this one. So maybe we can replace that guy, that sigmoid function, with the step function. That's it. And this guy is going to just resolve the issue of not having different derivative with the step function, right? At least for the step function, is going to help us. Clear? Now, if we do that, that's good. We have differentiation now. But the problem is that the output of the sigmoid function is not binary anymore, right? So if I replace this guy with the sigmoid function, this y here could be any number between 0 and 1. Yeah? This is not the same thing you wanted, right? You want a 0 or 1. How we can deal with that? Now here is the trick. You're going to look at this output. I mean, you interpret the output of your neural network differently. So you're going to look at this output as a probability. So it's a number between 0 and 1, right? So you're going to say this is the chance of my input being of class 1. Clear? So you're going to say sigmoid value is going to be, for example, here. So it is a number, a value. For example, here is 0.8. Then I'm going to say that this 0.8, I mean, of course, it could not be the label, but I'm going to say that this 0.8 is actually the probability of my true label being 1, right? So now I'm going to interpret this guy as a probability. And then this is going to just resolve the issue with not having binary output. But there is another issue here. And the issue is that how I can define the loss now. How can I define the loss? So don't show that yet. Let me write it down for you here. So I want to define the loss, and my output is going to be of the nature of probability, right? So what I see at the output is going to tell me what is the chance of my input being of class 1, right? But the true label that I have is the exact class, right? Now, if the exact class, if my V or VB equals, so let me say V is the class, is 1. So if I look at my data set and my class is 1, my label is 1, what is the probability of V being 1? I know it is a weird question, but answer it, please. If I am here, what is the probability I be here? 1. Great. So this guy is 1, right? So this is the probability. OK, this is not a good place to write it, so I'm going to write here. So when my label is 1, the probability of label being 1 is 1, right? And what is the probability of label being 0? It's 0 because it's 1, right? So now, instead of, look at it here, so V equals by 1, V equals by 1, so this is 1. I'm going to write it down V, right? Correct? Now, 1 minus V, correct? Right? Now, what's going to happen if instead of 1, V is 0? What is the probability of V being 1 when V is 0? 0. OK, V is 0, right? It's V itself, correct? What is the probability of V being 0 when V is 0? Is 1, which is 1 minus 0. So you basically can look at this label V to be again the probability of your data point being 1, right? But it's like the extreme case, correct? So your label is of nature of probability itself. Your output is of nature of probability. So now you can just compare them, right? Meaning that you're going to look at your output, and you see that it tells you that the chance of having 1 or being of label 1 is 0.5. And you see, look at your true label, that is 1. You say, no, the chance must be 1. So I'm going to modify all the weights so that it's going to increase this probability and get it close to 1. Clear? You got the idea? So this is how we can do it. So we are just going to change our interpretation. We are not training a neural network, which gives us the exact label, but we are just training a neural network, which is going to tell us what is the chance of being of label 1. And I'm pretty sure you do know how you can use that one to really specify the label, but we're going to do it again together. OK? So now, just make sure. What's the time? Oh, OK. Cool. We have lots of time. So now, now that I have just replaced this interpretation to my neural network, what I can do, I have my true label of the nature of probability, I have my output of the nature of probability, and then I can just compare them. But can I compare them with the indicator function? I mean, of course I don't want to do that. Yeah, it's obvious because I cannot compute the derivative. That's obvious. But even say one genie comes to me and tells me that I can compute that derivative for you. Does it make sense anymore to compute that one? To use that indicator function? No. And the reason is that the output of your sigmoid function is not going to be exactly 1 at any point, right? Just look at your sigmoid function here. I mean, if x goes to infinity, it's going to get to 1. But you don't have any value of x at which your sigmoid is 1. So it means that if you just use the indicator function, that the indication of output of a sigmoid not being 1 is always 1. Because it doesn't matter how big your x is. It's never going to be exactly 1. It's very close to 1. It's 0.9999999. It's never 1, right? So you never have this 1, so it's going to always give you error 1. It doesn't make sense to use it anymore, right? And on top of it, I mean, we just wanted to get rid of it at the first place because this is not possible to differentiate it. So now the question is that I have two probabilities. How can I compare them? And of course, you can come up with different ideas. Very simple idea is to just use the squared error, right? So you look at the output. You see what is the output is 0.6. Then the true one should be 1. So I'm going to just compute the difference and square it, right? It's a loss, right? And it's going to get minimized when this guy is exactly 1, right? Which is what I want. So this is going to be one choice. And if you use this one to compute your loss, then the empirical risk that you computed is going to be the mean squared error, MSE. Clear? So this is one choice. This is a very good choice because you can simply compute the derivative. Yeah? I can compute the derivative of this guy with respect to y3. It's simply 2 times the same term, right? Clear? And I have derivative. Everything is going to work in backpropagation. Clear? But this is not the best thing we do. The better choice is to use what we call it the cross entropy. And to just understand what the cross entropy is, look at these two guys. So I'm going to show this loss. This is cross entropy, the term between y3 and v. Okay? If v equals by 1, I'm going to write it down logarithm of 1 over y3. And remember, y3 is coming out of a sigmoid function, right? So it is between 0 and 1. So when is it minimized? When y3 is 1, exactly. If y3 is getting small and small and small, you're going to have larger and larger and larger logarithm of 1 over y3, right? So the minimum value you can see here when y3 changes between 0 and 1 is when y3 is 1. Because in that case, it's going to be log of 1 over 1, which is 0. Yeah? But any number smaller than 1, when you just reverse it, it's going to be larger than 1. And then when you take the logarithm, it is something positive. Correct? Everybody's clear? Yeah. Increase, exactly. So when v equals by 1, which is your true label, then you're going to put it log of 1 over y3. Okay? And this guy, when I minimize my loss, I just make it to be, I just try to make y3 to be exactly 1, which is my true label, right? Now, if v equals by 0, then I'm going to put it log of 1 over 1 minus y3. Again, when is this guy minimized? When y3 changes between 0 and 1. If y3 is 0, then it's going to be 1 over 1 again. It's going to be 0. If y3 is anything more than 0, between 0 and 1, then 1 over 1 minus that thing is something more than 1, right? And then the logarithm going to be something positive. So again, you're going to minimize this guy when y3 is exactly 0. So in the case that v equals by 0, then you basically just need to minimize this guy. And then the one which minimizes it's exactly y3 equal by v, which is 0. Yes?
Yeah, we didn't use the indicator just because we couldn't reach the exact one, or for example, something like that, yeah?
Yes?
Exact one or exact 0. So we go for a minimum, mean square error
Yes?
to have a both differentiable function
And
also
exactly.
But this function is again non-differentiable.
It's differentiable. It is. Why? You are taking differentiation with respect to y3.
I think the confusion is the fact that it's not displayed in its full form.
Yeah.
Yeah, I'm going to show it just in a second. But even in this form, you can take derivative, right?
They are the same,
Yeah, I'm going to give you v, right?
Yeah.
So if I give you v, it's either 1 or 0, right? Depending on what v is, you should take derivative of one of these terms. And both of them you can take derivative, right? So it's no differentiable. So now, if you look at these two terms, I mean, you can just compactly write it down in this form. Okay? So you don't need to have cases even. Because when v equals by 1, then this 1 minus v is going to be 0, right? Yeah? So I don't have the second term, I just have the first term. Here is 1 minus logarithm of y3 is logarithm of 1 over y3, right? Correct? If v equals by 0, then the first term is 0. The second term is multiplied with 1 minus 0, which is 1. So you can ignore that. And this is minus logarithm of 1 minus y3, which is logarithm of 1 over 1 minus y3. So that first line is exactly the second line. Okay? And that is the cross entropy function. Clear?
I have another question.
Yeah?
Why this function is better than the mean square error?
We're going to see it. Yeah? Yeah, this is a good question, and we're going to see it. Why? So this is again a loss function, and this loss function is again pushing or y3 to be the one which we want. Yeah? Yes?
I noticed that for all of the loss functions, so the input to the loss function is always the actual output of the forward pass algorithm and the ground truth. That's how I'm seeing this.
Sorry, once again?
So for all of the loss functions that you talked about so far,
Yes?
inputs are either are the expected output, which is the ground truth,
Yes?
and the actual output of the forward pass.
Exactly,
right?
exactly.
So I was wondering if you can define some other loss function that, for instance, maybe we want an algorithm that will give outputs that the outputs are as far away from each other as possible. So the input to the loss function is no ground truth at all. It's just the
But how you then, but the problem that you're describing, if I understood it right, it's not supervised anymore because you don't have any ground truth.
yeah, it's not supervised.
Yeah, then it's unsupervised learning, yes. This is like, for example, I don't know, k-mean clustering, things like that. But we are not talking about that yet, okay? So it's just supervised learning. So you do know that you have a ground truth, and then you want to get the ground truth. You don't care about distance, anything like that. Yes, this is supervised learning. So you do know what is, you always want your y3 to be exactly v. This is what you want. What you say is a different thing. We are not yet talking about it. We get quite late into that. Okay? So everybody's clear about cross entropy? Yeah? So now, some people wrongly call it KL divergence. This is not KL divergence, but you can compute KL divergence out of it, okay? So I don't want to complicate it, but just, I mean, if you hear this is KL divergence, that's right, that's fine. It's proportional to KL divergence, yeah, but it's not exactly that one. But anyways, now, the key point about this cross entropy is again that, I mean, first of all, we saw that this is really a kind of favorable loss that we want. And the second thing is that we can simply compute the derivative, right, I want to compute the derivative with respect to y3, so I basically compute the derivative of the first term. So this is v over y3 because log of x is going to be 1 over x, so we basically have v over y3, and for the other one is the same thing. Oh, here it should be plus. Sorry, it's a mistake. It's a plus, yeah. Okay, because I should, so just fix it. This is plus. I'm going to correct it later. Right? This should be plus. Okay? So, now, so we have the derivative. We are happy with that. And then a very valid question that your friend asked, why do we prefer cross entropy to the other one, the MSE? Why we do prefer that? And the main reason is that both of them are just, both MSE and cross entropy are pushing our output to be similar to our true label, but cross entropy is doing it much faster or much harsher. So just look at these two graphs. So here I'm just plotting for you this square term. Here I'm just plotting the cross entropy. Okay? And now, let's say that v equals by 1. Okay? If the output here, what you see on the horizontal axis is y3, the output of your neural network. If the output of your neural network is exactly 1, which is your desired output, right? So when it is 1, your loss here is going to be 0. And then when you reduce y3 towards 0, the loss is going to increase, which means that you are getting penalty, right? But the most penalty that you can get in this case is when y3 is exactly 0. And in that case, your loss is going to be 1. The penalty that you get is 1, right? But in the cross entropy case, again, here you are going to get loss 0 when y3 is 1. But when you reduce y3, you are just giving a very huge penalty, yeah? So if y3 potentially goes to 0, then the cross entropy in this case is log of 1 over 0, which is going towards infinity, right? So this guy is much harsher as compared to this one, and this is why you are more interested in this loss. It's differentiable, it is doing what you want, and it's just giving a hard penalty for any deviation from what you want. So it is a better loss as compared to the mean squared error. Same thing going to happen when you have v equal by 0. So again, both of them do the same behavior, so they are going to give 0 loss at point y3 equal by 0. But when you increase y3, one of them is just giving like larger penalties to your neural network. And this is going to just push your neural network faster toward the right output. Yes?
Why don't we use a loss like 1 over y or 1 over y squared, because it will be stronger than the log of 1?
Yes, but okay, this is a kind of valid question why we don't use 1 over y. But then the problem, I think, it starts with your derivative, because it's going to be 1 over y squared, right? So you want to just make it harsher, but if you just do it too harsh, then you could get into the trouble with gradient vanishing, because your gradients could be potentially close to the right solution, very, very small. Okay? You could potentially get that. Yeah? And then you don't want this. Yeah? But this is this is a kind of choice. You can come up with your own loss. And it's not like this is a kind of, there are losses which, even for simple problems, work better than cross entropy. But that improvement is very minor. And there is one thing aside, since I told you cross entropy is also called, is proportional to KL divergence. Since you are dealing with two probabilities, KL divergence is a kind of favorable thing, because it's a kind of convex metric of your probability distribution. Yeah, which is going to help you better when you do the optimization. You're going to converge your algorithm faster. Yep. Yes.
The loss increases. It means that we should select bigger step.
Exactly.
Gradient. So
No, it's not about learning rate. No, because your gradient is going to be larger.
Is there any possibility for using global?
No, it's not any issue like that here. So you have, I mean, if you just look at the loss function itself, both of them are convex. Yeah? So both of them, in terms of curvature, have the same behavior. The only difference is that when you get into the bowl, if you want to just move with the same learning rate, with cross entropy, your gradient is going to be larger because it's steeper, right? So then you are going to take longer step, but that longer step is not because of larger learning rate. It's simply because your function is taking you faster towards the minimum.
Yes, but I was wondering that if we select bigger step, is there any possibility for missing the global?
Yeah, but the point that I'm saying is that you are not taking longer step by your choice. Your loss is taking longer step, and this is no problem. The problem is when you take a large learning rate.
Is there any possibility for variation around the?
Everything is as before. I mean, those discussions that we had is correct for every sort of loss function. Yeah. So either you use MSE or cross entropy. At the end of the day, you need to just tune your learning rate. There's no difference here. The point here is that when you just do the training with cross entropy, you could just train your neural network with, I don't know, 50 epochs. With MSE, you need to do much more epochs. That's it. But it's not about like the step. That is not something that you artificially are changing. This is a point. I mean, it might be the case that, for example, the right learning rate with MSE, I mean, this is definitely the case that the right learning rate with MSE is different from the one with cross entropy. But at the end of the day, you put the same amount of efforts to find the right learning rate for both of them. The point, however, is that when you choose the right one of them is just going fast towards the minimum, the other one is just taking slower and slower to get to the minimum, right? And the one which is going very fast is the better one. Yeah? So you could, I mean, if it's hard to see it like in the very detailed version of the neural network, where if you just want to see the big picture, you can just look at these two graphs, and then one of them, I mean, if you just want to move from one point towards one, which is the minimizer here for the red curve, if you just specify your step size fixed, okay? In both of them, this guy is going to take longer steps, and after maybe a couple of iterations, going to get here. But this one is going to be much slower to get there. Yeah? This is the only reason. Yeah.
But then we can use this with a different learning rate.
Yes, but your learning rate is not being scheduled throughout the training. You just fix your learning rate.
Exactly.
Yeah?
But then let's say I use learning rate 0.001, so
Yeah.
20 with cross entropy. But then since the mean square is way smaller than that, we use 0.01 with 10.
Yes.
So a bigger learning rate, wouldn't that be the same at the end of
No, because you're gonna take your efforts to find out what is the right learning rate, right? Say for this one is 0.1, for this one is 0.01, right? It's okay. But then when you initiate that, you're not going to change your learning rate, right? Mm-hmm. But each time that you compute the gradient at every single point, your amplitude of gradient is also changing. That guy is going to get multiplied with your learning rate. And that is not in your hand anymore. You just had the choice to just specify your learning rate.
So that the cross entropy is a
finer way of just pushing your initial point towards the minimizer, of course. And then you should consider that you are doing it in a very huge neural network. So all of these discussions gonna just get scaled in a huge dimension.
So the little change in these stations will actually make it works compared to it's not works.
Not works and working or not working, but it basically help you just converge faster, for example, with cross entropy as compared to that one. You can train with this guy, but you might need to take more time to train your neural network. That's fine. I mean, any loss function that is just projecting your desire is going to work at some point, but how well it's going to work, this is a question of practice. So, any questions? Everybody's clear?
Yeah.
Yeah.
The question that my friend also asked is that when we are, for example, when we are in V1 and we are near to 0, the slope of a function is really high.
High,
So
yes.
we can get close to the real value sooner.
Fast, yeah.
Yeah, faster. And when we are also close to the real value, for example, when we are still close to 1,
Yeah.
the slope of this function is very higher than the other one.
Yeah, but
So we have to choose a very low learning rate.
no, but at the end of the day, the slope is going to get to 0, right?
Yeah, but
So-
this one near the zeros is still higher than the other one.
Yeah, of course, this is a good thing. It's not a bad thing. Because your curvature is, is smooth. You don't have such a thing, yeah? You have a smooth curvature, meaning that when you get close, as long as your learning rate is fine, when you get close to that optimal point, the gradient is just going to adapt itself to just move in right step size. The only thing is that you just specify the right initial scaling. That's it. Yeah?
But I think that we should be more careful when we are choosing the rating rate.
Here.
Yeah.
No, it's not going to be a big challenge. There is always a learning rate that's going to just make it diverge. The same thing going to happen for this one. It's only the value of number. Yeah? And you don't care. At the end of the day, when you train your neural network, you need to spend time to find the right value, right? So the amount of effort you put for both of them is the same. But once you choose the right value, then everything is in the hand of that loss. And cross entropy is doing it better as compared to the MSE. Yeah, this is the whole point.
Yeah. So this means that if we have the same learning rate for both of them, the convergence would be the same, yeah?
Not exactly the same learning rate, but if you choose right learning rate, like when you do, when you get to train your neural network, you start to do the validation, everything, and then you find out, for example, for this one, the right learning rate is 0.1. For this guy is going to be 0.0001. You don't care. But you still need to spend time to find that value. And once you find that value, then it's going to, after that, it's going to be loss function who is taking you towards the right minimum. Okay? Yeah. Okay. Just a second that I finish this, and if you have any question, then we can discuss it offline, because I guess, 5 minutes. Okay. So, so moral of the story, cross entropy is just pushing you faster towards the desired point. And because of that, this is a kind of better thing to choose instead of when you have the classification problem. And now, at the end of the day, if you want to just do backward propagation exactly, you can do exactly as before. The only difference is that instead of derivative of loss, which we didn't know what it is with indicator error, we are going to just replace it with the derivative of the cross entropy. Same thing again, if instead of the derivative of the step function, which again we don't have it, we just replace it with the gradient, the derivative of the sigmoid function. Clear? And then you basically have this backward propagation. So you start from your loss, and then you just do have this derivative. It is analytic. It is possible to compute it. And then you can keep on going backward till you get to your input. Okay? And now, if you just implement this guy is going to work. Okay? Now, one last thing is that you might say, okay, let's say that we did the training and everything is perfectly trained. Now I'm going to give one new point to this neural network. And this new point passes, I have trained, so I do fix now the weights here, here, and here. And now I put a new image, and this is the handwritten 2. And then I just pass it through my trained neural network. And then at the very output, I get the value, for example, 0.8. what should I do? How can I interpret that? Yeah.
Since it's close to 1, you just accept it.
Exactly. So when you want to use this neural network to infer for invariance, like you just look at a new image and you want to see what is the label that your neural network going to give this label, the output of the neural network could well be something smaller than 1. Yeah? It could be 0.8. But you can use the same interpretation as before. So you would say, whatever y3 is, this is the chance of having handwritten 2. And of course, 1 minus y3 going to be the chance of having something else, right? And then as long as this y3 is larger than 1 minus y3, you're going to conclude that this image is high probably the handwritten 2. So at the end of the day, you would say, OK, if y3 is more than half, like my neural network gives more than 50% chance of this input being handwritten 2, then this is I'm going to conclude or infer that this is handwritten 2. If it is less than that, I'm going to say no. So you can still use the output of that sigmoid to just test a new input with this neural network. Yeah? This is what you do in the invariance procedure. Clear? So now, I hope that everything up to this point is clear for you. Now, the thing that we are going to do on Tuesday is to just extend this idea to the case where we have multi-classes. Okay? So we don't have a binary classification anymore. We have a real one. Like MNIST, we have 10 different classes. And how we can extend this, we can simply project this idea of probability to higher dimensional probability, and this is going to be very effective. So we're going to talk about it this next Tuesday. So thanks, see you on Tuesday. So I'm going to upload the assignment 2 this week, okay? Assignment 2.